Welcome back. Today we continue in our series on reviewing distilling and wine videos together. We're going to learn, watch this, and discuss it down in the comment section. And feel free to let us know what you up to lately. What type of experiments you've been doing, what type of mashes, your recipe. Well, not your special recipe. You don't have to tell us that. But just get in the comment section and create a community together with a bunch of distillers.
Okay, so now let's review some of the principles behind the distillation in a laboratory setup. To begin with, distillation is not a discrete process. You don't take two fluids with different volatilities, mix them together, and then distill them and end up with pure 1 and pure 2. It's always a matter of favoring the movement of the more volatile fluid or vapor over the less volatile vapor. And you won't ever get a pure component. You'll always get a mixture of the two, but you'll favor or you'll concentrate the particular mixture based on when you sample or when you take the liquid out of the distillation or the distillate out of the end of the distillation apparatus. The process of distillation is based on the vaporization of the liquids. Alcohol, water, any kind of a liquid will evaporate over time. And the reason that occurs is because at any given temperature, the liquid temperature is the mean kinetic energy of the molecules in the liquid. But there are always a few molecules that are higher than average and a few that are lower than average. And those few molecules that have a sufficient kinetic energy to overcome the intermolecular bonds of the liquid will be able to escape the liquid. And because of the fact that they're leaving the liquid and they have a slightly higher kinetic energy than the average, there is an infinitesimal cooling of the liquid simply because we've left behind the less energetic molecules. That's why evaporation cools. It's more a selective elimination of the higher temperature molecules, leaving behind the lower temperature molecules. But at any given temperature, there's a certain amount of these molecules that are escaping and using up heat in the environment to produce that kinetic energy necessary to escape. More volatile fluids usually have lower intermolecular bond strengths, and as a result, they tend to evaporate at a lower temperature, but all liquids evaporate. The evaporation causes a vapor over the liquid, and that vapor is often described as the vapor pressure of the liquid at any given temperature. When that vapor pressure gets to the point, because of heating and increased escape of those energetic molecules, you eventually get to the point that the vapor pressure equals the atmospheric pressure, and that's the boiling point. And so the boiling point depends on the atmospheric pressure as well as the volatility of the gas. So for example, there is no boiling point of a liquid in a vacuum. I know it evaporates, but there's no specific point when the liquid's vapor pressure exceeds a vacuum pressure. It's always above the pressure of a vacuum. But in an atmosphere, with two liquids that are, say, mixed together, you're going to get a mixture of both liquid and a mixture of vapor above the liquid. And you'll get more of the higher volatility vapor above the liquid than the lower volatility liquid. As you warm the mixture, you still have that same ratio, but the pressures go up. Now, when we mix two liquids together, let's say we take alcohol and we take water, and we put them into a beaker. I'm going to take about 500 cc's of this isopropyl alcohol, and I'm going to take about 500 cc's of distilled water. Now these two liquids have different densities, and we use a hygrometer or a calibrated float to measure those densities. So if I take this hygrometer and place it in a calibrated cylinder and pour the alcohol in here, you'll see that the alcohol has to go to a pretty high level, and still the hygrometer is unable to float. This was designed to work with spirits, and so the alcohol here, the isopropyl, is around almost 200 proof, and it won't quite elevate the hygrometer. But if we take water and we place it in this cylinder. Because the water is a lot denser, the hygrometer will float much more easily. And using this type of technique, we can measure the concentration of a mixture both pre and post distillation. So what we're going to do is we're going to take these two fluids, the water and the alcohol, and we're going to blend them together in a large container for boiling.
I don't know. We ain't drinking this, people.
There's a little energy that is released when you mix two dissimilar liquids. As they blend, they give off a little bit of energy because they find new molecular partners. But that's sort of another point for another day. In any case, what we're going to do is we're going to heat this mixture. And the heating process takes a little while to get started. But once we get it going, oh, actually, I forgot to show you something, and I'm going to show that to you right now. I moved a little bit too fast. I'm also going to add to this a small quantity of what are called boiling beads. These are Pyrex reusable glass beads, and we're going to put them in the boiling flask to increase the surface area on the bottom, and this helps to augment or improve the rate of the boiling. Now, you don't need a lot of these, but what they do is they give more surface area for the particles or for the boiling bubbles to form on, and instead of getting large bubbles in the boiling and sometimes spray and debris thrown up against the sides, this helps to improve the boiling rate and improve the quality of the boiling process. Put a little clamp on here to keep these together. And then what we want to do is make sure that we've got this fixed pretty securely onto the hot plate. And then we're going to turn the heat on. Now, this will take a couple of minutes to warm up. But what's going to happen is we're going to begin heating the two liquids together. The vapor pressure will begin to increase. And then an interesting process happens in this long reflux column called a Vigreau column. I'll explain that to you in just a sec.
Hey, that thing sound like how the steel sound when it starts to warm up. That thump will get the thumping just the same. You know, liquor ain't too far behind that sound right there in the real steel.
Okay. So now that the liquid is boiling, what's happening is that the vapors are going up here, and as soon as they touch the glass, which is cooler here than it is here, they will become denser, heavier, and if they lose enough energy to the glass, they'll condense and drip down. But in the process, the glass warms a little bit. And progressively, as the molecules that follow behind find the glass a little bit warmer, they go a little bit higher before they begin to condense on a part of the glass higher up. The process of heating, vaporization, contact and cooling, and then dripping back down, this cycle is called reflux. And it occurs with both the water as well as with the alcohol. But the alcohol is always a little bit ahead of the water simply because it has a higher vapor pressure. And so there's more alcohol molecules that can go a little bit higher before they condense and drip down. These dimples in this Vigreau column perform the add additional surface area to improve the amount of reflux cycles that are occurring. There are columns that are meters tall that give you a lot more surface area for these cycles to continue to operate. But in all cases, there's always going to be some water mixed with the alcohol, and there's always going to be some alcohol left behind with the water. It's always a separation process that favors the more volatile molecules, but does not simply exclude the lower volatility molecules. As the cycle continues to heat the glass higher and higher up, eventually it gets to the point when it's at the top that some of those vapors will move down to the side arm here. And when they get to this point, rather than dripping down into the container, they drip down through the condenser, which has a central column that has the vapor moving through it, and then cold water that is on the outside that causes it to condense and then drip down into the container over here. Now the material in here is, it's about body temperature. But the point is, this is primarily alcohol, but it has a little bit of water in it. If we were to continue this process until all the liquid was gone, we'd end up in this flask with exactly what we started with in the first place. But if we stop the process, say, partway through, or we take out this beaker and we place another beaker in place of it, so that the next sample has a slightly different mixture of alcohol and water. As we continue on, the mixture will constantly increase in its percentage of water and decrease in its percentage of alcohol. And the only way that we can really provide separation is to either keep taking off samples or stop the process partway through. The whole process of distillation, though, is never really complete. Even at the bottom of this flask, we're going to end up leaving some alcohol behind. And even the very first drops that came out of here have some water in them. But the percentages are substantially different. And what we'll do is, once this distillation has completed a little bit further, we'll measure the specific gravities on the first liquid that we got out and the last liquid that we get out, just to show how the different density of the liquid can be used to measure what the percentages of the different components are. All right, now what we're going to do is I'm going to finish by throwing out this middle component. And then everything I save from this point on is going to be the last part of the distillation. Remember, I put 500 plus 500 or 1,000 cc's in. So I have about 300 from the first cut, and I have about 300 from the middle, which should be sort of a blend of the two concentrations. Then we'll get about 300 here, and then we'll measure the specific gravity. As you can see here, the temperature is now almost to the boiling point of water. So mostly what's boiling in here is water. An interesting thing about water is that it takes more than 5 times as much energy to convert 100-degree centigrade water liquid into 100-degree water vapor as it takes to heat that same quantity of water from freezing all the way up to 100 degrees centigrade. It's probably the most energetic liquid in terms of the requirement to break the intermolecular forces that keep the water molecules together. As a consequence, it takes a lot of heat to break those bonds, and therefore, even though we haven't changed the setting on our boiler, you can see that the boiling seems less vigorous. The flow into the collection cup is slower. We haven't changed anything about the heat, it just takes a lot more heat to boil the water. All right, now for the test. What we're going to do is we're going to take the first liquid that came out of the still and place the hygrometer in here. Now remember, with the pure isopropyl, we couldn't even float it. Barely able to float it. So there is a little bit of water in here as I described. All right, now let's take this. Let's take the sample that we're still distilling. Let's see how this does. So as you can see, this is floating really, really well. It's essentially zero proof. There's really no aroma of alcohol. Can't even taste it. There is some, probably 1%, 2% or so. But this is the end cut from here, and as a result, there's going to be very, very little alcohol in there.
It's gonna get in your mind.